All right, so we've already talked about identities a little bit earlier in the semester. So what this chapter is going to focus on are a couple of different things. One is how to verify that an identity actually is what we mean it is, when that actually is true. And two, some new identities that will be useful later on, in particular in calculus, that you'll want to make sure that you're aware of and know how to deal with. So first, let's talk about what we mean by an identity. So an identity is an equation. First and foremost, it's an equation. Okay. Now, usually, when you are dealing with equations, you're looking at something like this first one, very simple type of equation, right? But usually, when you think of an equation, you think about solving one, right? That's not what we mean by an identity. It's not something that we want to try to solve. It's an equation that's true, that is always true, no matter what value we plug in for the variable. Oops. If I can spell, plug in for the variable. And I'll put in parentheses and have everything defined. If you plug in a value for the variable and it makes an expression undefined, we don't worry about that in terms of whether or not the identity is true. So we don't worry about things where you would have undefined. For example, remember for tangent, we can't plug in pi over 2. We wouldn't worry about that at all. Okay? That's what I'm saying by and have everything be defined. We're only worried about values that we can plug in for the variable and everything be defined. There you go. All right. So that first equation that I just alluded to a minute ago, would this be an identity? Is this always true no matter what we plug in for x? No, right? In particular, what value do you have to plug in for x in order to be able to get a true statement? A 3, right? So we refer to this type of equation as a conditional equation. Only true for specific values of x. In this case, namely, x equal to 3. Conditional equations are the ones that you're used to solving, right? Try to figure out what x is. That's what we mean by a conditional equation, okay? That's not what we're doing with identities, okay? Let's look at the next equation. Is this an example of an identity? Is this true no matter what you plug in for x? Yeah, because notice if you multiply this out, this is exactly what you get, right? So this is an identity. It's an algebraic identity, but it's an identity. It's an identity because it's just we obtain the right-hand side from the left-hand side just by doing distributive properties, right? And the last one, is this one that we've seen before? It's one of the Pythagorean identities, isn't it? Right? The reason why I put this one on here is that I want you to note that when theta equals pi over 2 plus n pi, tangent of theta and secant of theta are undefined. But that doesn't matter in terms of identities, okay? Usually, the kind of quick way to say things is an identity is true no matter what you plug into the variable. There's that little bit of a caveat in there that says it's true for anything you can plug in and have it be defined. Okay? So I cannot, this is not a true statement when I plug in pi over 2 because I can't plug in pi over 2. Okay. So there's not anything to say because it's not a well-defined statement at that point. Does that make sense? I'm making a bigger deal out of it than it really is for our purposes. Okay. But we typically will say it's true no matter what. That's not quite right. It's true no matter what, as long as it's defined. Anyway, I won't harp on that anymore. All right. How do we verify that things really are identities? I have no idea why I put a question mark at the end of that header. Well, how do we verify things are identities? Or how do we prove something is an identity? So there are some tips that we'll follow. These aren't hard and fast rules. Actually, some of them are hard and fast rules. These are not hard and fast rules in general, but these are just some tips that you might want to follow. The first one is only work on one side of the equation. And I'm putting equation in quotes on purpose. When you're asked to verify or asked to prove, those two words mean the same thing in math. If somebody says verify and somebody says prove, they literally mean the same thing. When you're asked to verify an identity, it's stated as an equation. However, you don't know that it's a true statement yet. So it's not like other equations that you're used to solving for, where you're trying to, say, isolate the x. I cannot operate on both sides of the equation because I don't know that I have an equation. Okay? So multiplying both sides by the same thing, can't do that. Squaring both sides, can't do that. Okay? You have to work on one side. Okay? We cannot try to do things to both sides because I don't know that I have two sides. Okay? So that's important. This one you have to follow. Okay? You cannot do things to both sides at the same time because you don't know that you have two sides. You don't know that it's an equation. Okay? That's a big one. All right? Pardon me. Second one. Work with the more complicated side and try to make it look like the simpler side. So what I mean by that is it's typically a lot easier to put things together than it is to tear things apart. Okay? So to give you an example, is it easier to multiply 15 and 17 together than it is to try to figure out how to factor something into 15 and 17? It's a lot easier to multiply than it is to factor, right? Okay? So if you've got an operation where you can put things together, that's easier to try to work with than having something already together and trying to tear it into two pieces or multiple pieces. Okay? So you usually, not every time, but usually you'll see one side, lots of stuff, other side, not a lot of stuff. And so you'll work with a lot of the stuff that's a lot of stuff and try to put it all together. Okay? The third one, pardon me, I forgot what I was going to say. Oh, the third one, substitute known identities for other expressions. Oops. What do I mean by that? So maybe you have an expression that looks like sine squared x plus cosine squared x. And you have that in what you're trying to simplify. Well, what could you replace that with? What do we know that sine squared x plus cosine squared x equals? 1, right? So this is what I mean by doing substitution. I see this expression, I replace it with a 1. Okay? Now, sometimes it's not written in this exact same form. If you had something like 1 minus cosine squared x, what could you replace that with? Sine squared. Good. And notice this is an example, kind of a small example, if you will, but it's an example of something that's complicated and replace it by something simpler, right? So taking a more complicated expression and making it simpler. Okay. So one of the things that, again, that helps us do that is to substitute known identities, okay? So here in a minute, we're going to list out some known identities that we have that we'll want to keep track of, and that'll help us in our deliberations as we go through. Pardon me. I'm so sorry. Another thing, and this actually gives me another example here. Sometimes you have to be a little bit creative to get some known identities. So one of the things you might want to look for maybe are differences of squares. Or maybe even create differences of squares. What do I mean by that? Well, let me take you back to maybe an example that you did back in algebra class, and then see how that ties into trigonometry class. What if you had something like 1, or let's say like 4 minus square root of 3 in the denominator? And you were asked to rationalize the denominator. This is probably something you've done back in an algebra class at some point. Do you remember what special thing you multiplied top and bottom by to get that irrational number out of the denominator? The bottom. So you multiply the top and bottom by the same thing, and looking at the bottom. So notice what I'm trying to get to. Notice I said differences of squares, right? Okay, so remember how your difference of squares factors? How does a squared minus b squared factor? Good, right? Oops. I don't know why I wrote the minus sign first. Yeah, factors as like a plus b and a minus b, right? So notice when you take this this thing that has a plus sign in the middle, and this thing with a minus sign in the middle, it squares the individual terms like this, right? If I want to get rid of that irrational number here, it'd be nice to square this thing, right? Right? I can't just square one piece. I can't just square a fraction and keep things equal either, right? But if I look at this form, I've got a minus b. What might I want to multiply to be able to get rid of that root 3? Yeah, 4 plus root 3. Good. I have to do it on top and bottom, right? And the reason why we do that is because now you get 16 minus 3 on bottom, right? Squares of the first piece, squares of the second piece, right? By the way, they call this rationalizing the denominator. There's nothing special about rationalizing the denominator. We can handle irrational numbers in the denominator. The process is doing this rationalization or multiplying by this special form. Do you remember what the special form is called when we just change the sign in the middle? That's a special name. Starts with a C. Conjugate, yeah. These are conjugates of each other when you flip the sign in the middle. So how does this apply to trig? I said look for differences of squares. There's I got this 1 minus cosine squared, and that's simplified to sine squared, right? This is a difference of squares, isn't it? Sometimes you might see like a 1 over 1 plus cosine x. In order to see a difference of squares, what should I multiply by?
1 minus cosine.
Yeah, 1 minus cosine of x. Do that conjugate idea, and you get 1 minus cosine squared x, and now what do you get in the denominator? We get a sine squared x, right? So if you've got something without a square in it like this, maybe one of the tricks you might try is to multiply by a conjugate and see if you get a difference of squares. All right. The last little tidbit of information I can give you is when all else fails, convert everything to sines and cosines. If you've got things with secants, cosecants, cotangents, and tangents, and you don't know where else to go, just make everything sines and cosines and see what happens. Okay? A lot of times that will give you some things to play with. All right, so let's see if we can start putting some of these things to work. In order to be able to put some of these things to work, we need some fundamental identities to help us do some substitutions later on. So the Pythagorean identities again, we've talked about those before. That was the big one, sine squared x plus cosine squared x equals 1. Remember, we can convert the other two just by dividing both sides either by sine squared or by cosine squared. Gives you the other two. So you get tangent squared x plus 1 equals secant squared x, or 1 plus cotangent squared x equals cosecant squared x. Those are the three Pythagorean identities. It's important also to be able to manipulate these things around. For example, I've already written as an example, if you have 1 minus cosine squared, you get sine squared, right? Or if you did secant squared minus tangent squared, you get 1, for example, right? It's important to recognize the manipulations. It's also very important to recognize what aren't manipulations. For example, if you had sine squared x minus cosine squared x, that's nothing. Right? Not at least in terms of these, it's nothing, right? So be careful with those. Like secant squared plus tangent squared doesn't work. Okay? So make sure that you know what these say and make sure you know what these don't say. It's important. The reciprocal, or maybe even better in terms as ratio identities, are just the ideas of being able to write these in terms of sines and cosines or the reciprocals of each other, right? So secant of x is 1 over cosine. Cosecant of x is 1 over sine. Cotangent is 1 over tangent. And then, of course, you also have your ratios of tangent is sine over cosine, and cotangent is cosine over sine. We know these, right? But we're just reminding ourselves, or having them in a convenient place while you're practicing, so you don't have to go look them up all over the place. The co-function identities, remember, refer to the complements, right? So pi over 2 minus x is 90 degrees minus x. That's the complement of x, right? And the co part refers to the complement. So cosine of pi over 2 minus x is sine of x. And it also works the other way around. If you have sine of pi over 2 minus x, that's cosine of x. Likewise, if you have cotangent of pi over 2 minus x, what's that going to equal? Tangent, good. Yep. Those are the cofunctions. And then vice versa as well. Cosecant of pi over 2 minus x will be secant. Good. And then vice versa as well. You don't have to draw this triangle. I just want to remind you why this is true. If I have a right triangle and this angle is the right angle, if this is x, then up here is what? Let's measure this angle up here. It's 90 minus x, right? Or the pi over 2 minus x up here. Notice that the opposite side for x is what for the complement? The opposite for x is the adjacent for the complement and vice versa, right? We agree? That's why those are identities, correct? Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. The hypotenuse doesn't change for each of them, right? But the opposite for one is the adjacent for the other, and that's why you have those cofunction identities. And again, that's why they're called the cofunctions, right? By the way, is because they deal with the complements. That's where the co part comes from, is complement. Even and odd identities have to do with algebraic properties of even and odd functions. Remember that even and odd are symmetry ideas. Even means it's symmetric about the y-axis. Odd means it's symmetric about the origin. Sine's an odd function, so sine of negative x is negative sine x. Tangent is odd. Cotangent is odd. And cosecant is odd. Oops. Odd. So for each of those four functions, it looks like you pulled the negative out. Please do not think of it that way. That's not what we're doing. Because if you think about it that way, you're going to end up with like a 2 in here and try to pull the 2 out. Okay, this is not a pulling out of a constant. Okay, this is the fact that the graph of it is odd, right? Again, odd graphically means if you rotate it 180 degrees, it looks exactly the same. Okay. So please do not think of this as pulling out a constant, because that is not what's going on. I know it looks like what's going on, that's not what's going on. Remember, this is not multiplication, this is a function, right? This is the input of a function. Okay. The other two, cosine and secant, I said them both at the same time, are even functions. So the negative basically just goes away. And again, this is another reason why you should not think about the first ones as just pulling out the negatives, right? Because it doesn't work for these two in particular. And if you change that number on the x, that argument, to a 2x or a 3x or whatever, it never works. You can never just pull out a constant. Okay, so please do not think about the first ones like you're doing that. The reason why I'm making such a big deal out of that is because we're going to come up and have identities that actually do tell you how to rewrite things with ones like 2x or an x over 2 or those kind of things. Okay. And so I want you to make sure that you don't just try to pull the constants out. All right. Let's see if we can start applying some of these principles to some of these examples that I have in here. So let's look at this first one. We want to prove the identity. Again, prove or verify means the same thing. I have prove in here, but if you see in anything else that says verify an identity, it means the exact same thing. Okay? So we have tangent of the opposite of theta, pardon me, plus cotangent of the opposite of theta is the opposite of secant theta's cosecant theta. All right, so again, I need to work on one side and make it look like the other. Okay? And I already told you, work with the more complicated side and make it look like the simpler side. And I also said that it's a lot easier to put things together than to tear things apart. All right? Agreed? So based on that, which side do you think you want to work with, the left or the right? The left, right? I've got a plus sign in the middle, correct? It's going to be a lot easier to try to combine the plus sign together than it is to take that multiplication and try to break it into a sum. Right? Okay. So let's start with the left-hand side and see if we can combine it to make it look like the right-hand side. All right, probably the first thing I notice is that I've got opposite of theta on both of those things, right? Agreed? So of that list of stuff that we just made a minute ago, what might apply?
Replacing it with a negative tangent of theta plus negative or minus cotangent of theta.
Good, yep, exactly right. I can use those even-odd identities to replace tangent of negative theta with negative tangent theta and cotangent of negative theta with negative cotangent theta. Yeah? All right, so again, the reason why we picked the left-hand side, pardon me, the reason why we picked the left-hand side was because there was an operation that I can actually use to combine these two things. However, currently the way they're written, it's a little hard to combine them, right? So how might we rewrite one or both of those so that we can start to think about how we might try to combine them into a single object? What might you do with one or both of those functions? That sounds like a good plan to me. If you're stuck and don't know where else to go, and you've got things that aren't in terms of sines and cosines, put them in terms of sines and cosines. It's okay to get stuck. It's not okay to say, I'm stuck, and you have a tangent in there, for example. Because I can always write tangent as sine over cosine. Okay? Again, it's okay to get stuck and have a problem and I need to ask a question. That's perfectly fine. But your stuck should never be, I have stuff in there that I can convert to sines and cosines. Because if you don't know where else to go, try that first. Okay? All right. How does that help? Well, we've converted both of these into fractions. How do you combine fractions? What do you do? If I want to add or subtract fractions, what do you need to get? Common denominator. Good. So what should we multiply the first fraction by? Sine theta over sine theta. Good. And the second one? What should we multiply the second fraction by? Good. Yep, I need to multiply the other one's denominator, right? Better do cosine over cosine. So we did that to get common denominator of sine theta cosine theta, right? That is the common denominator now. What is your numerator? Good. Exactly right. So the first fraction has a minus sine squared theta, and the second one has a minus cosine squared theta, right? Agreed? What can you factor out of the top? So I need to do one more thing before I make it equal to 1. You're right. What way can I factor out of the top? -1? Good. Factor out the negative. We get sine squared theta plus cosine squared theta, and that should be one that you recognize immediately, right? We're almost done. We were at -1 over sine theta cosine theta. But that's multiplication. So if I move them back up to the top, 1 over sine is the same thing as cosecant, and 1 over cosine is the same thing as secant. And isn't that where we wanted to end up? Yeah. Don't lose your side of the forest because you smacked into a tree. Keep track of where you're going, right? We know where we're trying to end up, so end up there. Okay. Right. Notice again, we did not try to operate on both sides, right? We took one side and worked until we got to the other side. This is how we verify an identity. What questions do you have on this one? This one was a pretty good first example because, again, we took a more complicated side, try to make it put together to get to a simpler side. We used known identities in that first step, and in the next to last step, we also got stuck a little bit and said, okay, I'll convert everything to sines and cosines. Right? You could have, in this second step here, you could have just rewritten cotangent as 1 over tangent and then got your common denominator as well. And got to the same place. Might even get a little bit faster, but good at the same thing. It's okay. Let's see if we can do another one. We got 1 over 1 plus sine x plus 1 over 1 minus sine x. And that says that's equal to 2 secant squared x. Which side do you think you might want to work with, the left or the right? The left, right? That one's a lot more complicated, correct? So start working on that one. Work on it for a minute or two. And see what you can come up with. Ready to talk about it? Yeah? All right. All right, now there's not a lot of substitution we can do, right? Everything's already in terms of sine. So change everything to sines and cosines is not really helpful. And there's not a known identity to replace 1 plus sine x and 1 minus sine x with, right? Not a lot of place to start. However, I do have two fractions that I want to add together. So what do you think we might want to get? Common denominator, right? I've got two fractions that I want to add. I better get a common denominator, right? There's not a lot of other things I can do algebraically. I don't have, or trigonometrically, I don't have any identities that I can plug in, and I can't flip things around because I got a sum in the denominator. So there's not a lot I can do. I'm kind of stuck, right? We can't split up over a sum or a difference in the denominator. We're kind of stuck, except for being able to get a common denominator. So what do we need to multiply the first fraction by? 1 minus sine x over 1 minus sine x, and the second one? Yeah, 1 plus sine x, good. So we've got a common denominator of 1 plus sine x times 1 minus sine x. What do you get on top? 2, right? Because you get, I'll just write it out, 1 minus sine x plus 1 plus sine x, right? So we get when we add the numerators together. So the top is 2. What do you get when you multiply out the denominator? What do you get when you multiply out the denominator? Yeah, remember I said look for those differences of squares, right? When I take 1 plus sine x and 1 minus sine x and multiply them together, I get 1 minus sine squared. Notice we haven't done anything but algebra so far, right? Haven't done zero trig. So far, this is all algebra, right? Got a common denominator, simplified the numerator, multiplied out the denominator. That's nothing to do with trigonometry. All right? Here's going to be our first step of trig. What can you replace 1 minus sine squared with? Cosine squared. Good. That's our first step of trig in this entire problem. This is 2 over cosine squared x. Here comes step number 2 of trig, and then we'll be done. Cosine squared x is in the denominator. If we move it up to the numerator, what does it become? Yep, 2 secant squared x. Yep. So notice most of this was algebra, right? We added two fractions together, got a common denominator. So, I'm sorry, we wanted to add two fractions together, so we got a common denominator, added them, simplified as much as we could, and said, oh, hey, I recognize the denominator now as something else trigonometrically, and then moved it up again using another trig identity. Questions on that one? This one, I think there was really only one way to go, okay? Again, it would have been a lot harder to work this in reverse and try to split things up, right? I really think there was only one way to go on this one, okay? Work with the left-hand side and do literally this to get to the right-hand side. I mean, technically, you could start here and work backward, just a little bit harder. All right, and the next one, I think we've got a few different paths that we could actually take to get this identity verified. Again, looking at the two sides, which side do you think you might want to work with? The left, right? There's more stuff on the left than there is the right, correct? This one, I really do think you've got a few different avenues that you could go down to verify this particular identity. first, let me ask you this. Do you see anything you're going to replace the numerator with? Do we know anything that's 1 plus tangent squared is equal to? Secant squared x. Good. Right? That could be step 1. I want to try to get to cosecant squared. At this point, I probably want to try to just go ahead and convert everything to sines and cosines. That's probably easier. At least I think that might be easier. Secant squared is cosine. 1 over cosine squared, and tangent squared is sine squared over cosine squared. And now you're dividing by a fraction, so we can multiply by what? Yeah, by the reciprocal. Good. Anything good happen? Yeah, cosine squareds cancel out, right? You're left with 1 over sine squared x, which is the same thing as cosecant squared. That okay? Okay, but there's another way we could have started this. This does require us to break. I mean, there's actually 2 other ways. I think I could start this one that would kind of follow along the same lines of what we've been talking about. This does involve us breaking something apart. Notice I've got a plus sign in my numerator, so I could break this up into 2 fractions, right? I could break this up as 1 over tangent squared plus tangent squared over tangent squared. Break it up. Tangent squared over tangent squared is going to be 1. 1 over tangent squared can be rewritten as what? What's 1 over tangent the same thing as? Cotangent, yeah. And now do you recognize an identity for that one? Yeah. So the reason why I put this particular example on here after the previous one is because it kind of illustrates 2 different things. That previous one, I think there was literally one way you were going to go, right? This one illustrates that there's a couple of different paths that you might have wanted to try. And both of them are perfectly valid. Another thing that you might have tried just to start off is, I see tangent everywhere, I might just convert it to sines and cosines and start there, which would have also been perfectly valid. Okay? For example, I'm going to write this on the board rather than on the screen. But for example, if you would have started with this, you might have then chosen to multiply both sides by top and bottom by cosine squared x to cancel the cosines out. You would have got cosine squared x plus sine squared x over sine squared x. And then what's the top equal to? 1. This would be a third way that you might have tried to do it. So the moral of the story is, in this particular example, which is why I put this one on here, is there's no one right way to do the problem. Okay? Even though the previous example was pretty much there was one way you were going to go, this one I can see at least 3. Okay? So the best advice I can give you when you're trying to do these things is just keep your hand dirty and try to see what happens. Okay? Math, a lot of times you're presented math very, 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 very disingenuously. We start at point A and we elegantly move all the way to point B. That is not how math is done at all. Sometimes you start at point A, then you play around with point B and try to work backward, then you're on to point C, and then you wad up 8 pieces of paper and throw it away and start over again. Okay? What you see is a very, very polished product at the end. Well, maybe when I'm teaching it's not so polished. But what you see is a very, very polished product at the end. That is not how math is done at all. Right? So keep that in mind when you're trying to play around with these problems, is that get your hands dirty and play. And then at the end, just try to write it up pretty. Okay? Have a good one. We'll see you on Friday.